And what we're going to discuss now, I'm going to do a short introduction of the topic, and then we're going to cover two different models, the discrete exponential model and the gamma continuous model. And we'll see that actually this model right here, the exponential model, is just a simplified version of the gamma model, where alpha is equal to 1, a little bit high level. Okay, and the first thing we would like to answer is, why are we actually doing, why do we actually need gamma distribution models? And why are we in the first place doing heptanes plus characterization, this is all kind of related to. So the first thing to note there is that it's impossible with chemical separation techniques to identify the C7 plus components individually. And even if they were identified, it would not be actually possible to measure the critical properties and other EOS parameters for the fluids with that's heavier than C, 20 plus or something around that number. And this problem is solved practically by making approximate characterization of the heavier compounds with experimental and mathematical methods. Yeah, the give control. Yeah, this part. Yeah. I think that's clicked somewhere. No, there we go. Thanks. Sorry about that. And we understand the reasoning behind that. If we, for instance, look at C14, what's reported in the laboratory as a nice, clean, single carbon number C14 can actually consist of up to close to 1900 different isomers. So what we're actually trying to capture for a particular field is kind of the average C14 component. And when we are actually doing heptanes plus characterization, which is after we've done all the QC work that we've been talking about so far, we jump into this heptanes plus characterization, which is a very, very important step before we do EOS predictions and tuning of the equation of state. So the approximate procedure can be split into 3 main tasks, where the first one is dividing the C7 plus component into a number of fractions with known molar compositions. That's where we are going to talk mainly about the gamma distribution model. And then we will, as we will also talk about here, when we've been talking about that a little bit already, is to define a relationship between molecular weight, specific gravity, and boiling point of each fraction. So this is actually exactly what can be measured in a TBP experiment, so an ASTM distillation type experiment. And also this plot that we just talked about is related to number 2. And then the last point is actually estimating the critical properties based on a wide range of different correlations. These critical properties such as TC, PC, eccentric factor, volume shifts, and BIPs, which we at this point we don't know, or we assume that we don't know what these properties are and mean, but that's the topic of the next section, so we'll get to that. And when we are talking about modeling of C7 plus distributions, we are mainly internally using a gamma model, which is the most generic model for these purposes. And I remember back in the days a few years ago, I asked Curtis of all the papers that he wrote, which paper was he the most kind of satisfied with. And this paper, I think from 83 or 84 on C7 plus, modeling C7 plus distributions. Can't remember exactly the name, but about the gamma modeling approach was, at least at that point, the one that he pointed out as being the most time appropriate, and I guess also widely adopted by the industry. Any comments on that, Curtis?
Yeah, 1980 was actually when it was presented. We got it in the journal. It took 3 years in 1983, and I mean it was timely because the laboratories only gave C7 plus properties and amount. So between then and now, when you get 40, 50 components, and then when you got always the same 11 components with no resolution on this very important heavy C7 plus, I think that's probably why it was so timely. So.
Very good point.
And we can upload the paper and that's happening plus characterization.
I think it's already uploaded there, 83 paper from Curtis. And Bill will go through this in detail in a little bit, but and this is a figure from the SB monograph that is also uploaded in the course material, just showing a few different versions of the gamma model or with different shapes essentially, and also yeah. And the model is from a high level perspective requires 3 input parameters: an average molecular weight of C7 plus, which typically is sample specific, a bound, a lower bound, and a shape. And when we do, like, let's say we create the equations of state for the Bakken or Vaca Muerta or Permian or a big field like that, we usually try to find field specific shapes and bounds. So they are, call it constant, these parameters for a particular field, while the C7 plus is sample dependent. So if you're talking about a gas condensate fluid, that will have a much lower molecular weight of the C7 plus and a higher API, versus a black oil, maybe even from the same field, that would have a much higher molecular weight of C7 plus and lower API. So this is sample specific. But when you hear about the gamma model, just think that these 3 parameters is required here. And here we just see an example of a molecular weight C7 plus of 200, or an average molecular weight, and the bound of 90, showing a shape of 0.5. A shape of 1, which is this one special case of the gamma model, which is essentially the exponential model, and then an alpha equal to 2, which, for instance, could be a biodegraded oil, I guess. So having like a hump like this. So this could be biodegraded oil, not very pretty. We can mention that for those of you who are working on conventionals, we have found there to be, typically alphas, depending on what field you're in, maybe between 0.55 to 0.7. The straight line here is what's default and the only option you can use in, for instance, PVT sim. So that's the exponential model that we'll talk about in a little bit. And the ranges for alpha is typically between 0.5 to 2.5. And as I just mentioned, the alpha equal to 1 is the exponential distribution, which is what is recommended in general if no GC or TBP data is available. The bound that I just introduced can be physically thought about as the minimum molecular weight that can be found in the distilled fraction of C7 plus. And that number is typically 90 or close to 90 in general. Okay, so on that note, I'll just give the word to Bilal.
Okay, so now actually we will go through in more detail about the different Molar distribution models that Matthias briefly mentioned. But before that, we just tried to go through why we are talking about Molar distribution models. And as Curtis said that in 1983, like PVT labs, that they used to measure like C7 plus as one component, and then there was essentially no resolution on the heavier ends of the C7 plus fractions. And there it was very at that time the Molar distribution models was a big deal, and it was really needed for proper equation of state model development, because you needed more information on the C7 plus fraction. So first, that Molar distribution models, what do? They actually describe the distribution of the amounts of Cn plus fractions, and Cn plus could be a C7 plus or C10 plus or C11 plus, depending on what kind of GC data you have. So normally now, if you have in the GC data, we have like these isomers for these lighter fractions. We saw before, like for C7, you have benzene, toluene in for C8. So when these isomers are reported, then generally your Cn plus is the C10 plus or C11 plus. The carbon number from where the single carbon numbers actually start in your GC data. In the absence of extended GC data, so that was the case in 1980s when there was no extended GC data available, and we only had this Cn plus as C7 plus. We didn't have any more resolution on the heavier ends. In that case, you needed some kind of model to give you the molar distribution of C7 and heavier fractions into the equation of state model, where your heaviest component could be C36 plus or C30 plus, etc. So at that time, when we didn't have the extended GC data, this was the real use of the molar distribution model. But now, when we look at the PVT reports and we get the GC analysis, we get the extended GC data usually, and we get the data until C30 plus or C36 plus, and we know that even though that data is measured in the lab, that data has uncertainties due to reasons that we discussed before, like mainly baseline shift and internal standard in the flash oil. And in that case, the molar distribution model nowadays, it is a very good tool to quality check your lab reported compositions. And in that, so what generally we do, we generally develop a field-wide gamma distribution model, tuning the good quality lab reported extended GC data. And then this tuned model, it can help us to QC any bad quality GC data, gas chromatography data, and systematically we can replace any bad GC data with reliable estimates from the model. And we will see some of the examples of this in the coming slides. So now we have two kinds of models. So one is the discrete exponential model, and the other is continuous gamma distribution model. And we will see why with the exponential model we are saying it's a discrete, and continuous with the gamma model. So first we can discuss the discrete exponential model briefly. So this exponential, it's a discretized exponential model, and that's why we call it discrete, because it's only applicable to single carbon number fractions. So you cannot use the model to describe the molar distribution of the heavier ends if you don't have single carbon number. So let's say if you have TBP data with non-single carbon number cuts, let's say you have TBP data with only the cuts that are representing different refinery cuts, like gasoline, for example, or light oil, heavy oil, these kind of cuts, then you cannot use this discrete exponential model to describe the molar distribution of those heavy ends. The other limitation of the discrete exponential model is that the difference between the consecutive component molecular weight, so I plus 1 and I, it should always be 14. So if we have a component C7 and C8, then the difference between the molecular weight of these two components should always be a 14 number, which may not necessarily be the case in the real life. And this again, the exponential model, as the name suggests, that it's only valid for exponential distribution, which means that if your data falls on a straight line, if you plot the log of Zi versus Mi, then your data should fall on a straight line, and this is usually reasonable assumptions for C8 plus or C10 plus extended GC data in most petroleum mixtures. But what we have found that generally this distribution is not exactly exponential. And as Matthias was saying, that like in the gamma distribution model, if you use alpha is equal to 1, that's exponential. But what we have found, at least in the unconventionals, that alpha is generally a 0.5 to 0.7 value for C7 plus. So yeah, and surely for biodegraded oils, and if you want to describe the molar distribution of oil-based muds, then you cannot use the exponential model, because that data for biodegraded oils, that this distribution of the C7 plus, it's never on an exponential distribution. Yeah. Okay, so now we can just look at briefly on the model, and that's also in chapter 5, I guess, in the monograph. So what the model, so how the model looks like. So this is the expression of the model. So Zi with a hat, that's the normalized mole fraction of a component. So that's how this is the normalized mole fraction. The mole fraction of the component divided by the Cn plus or a mole fraction, which could be like, for example, C7 plus, the total C7 plus mole fraction. So that's this number here, and this is the normalized mole fraction of the first carbon number from which we are using the model. So this could be, if we are using like for C7 plus fraction the model, then this will be the mole fraction of C7 carbon number itself. And then A is generally representing the slope of the straight line in the exponential model. So that's this number here, and in the model, this is this normalized mole fraction of the first carbon number. This can be calculated with this equation here. So if I replace this whole term into this term A, you will see that A, which is kind of slope of this exponential model straight line, it is mainly a function of this number here, which is the average molecular weight of the C7 plus, for example. And then H is actually a constant. You will see what it is. And N is just the carbon number from which we are starting. So the model starts from N plus 1 until N minus 1. For example, N is it could be C7, for example. And also this the molecular weight of each component, that's given by this equation here. Mi is equal to 14I plus H, and which again suggests that this delta M, the difference between the two consecutive component molecular weight, should always be 14. That's why this assumption comes from here, because the individual component molecular weight has to be given by this equation. And H is a constant, and PVT sim by default, I think it's -4 value. And what H is actually suggesting, so if we just take one expression here, so if we take this expression, so this is the normal paraffin molecular weight of carbon number I, and this is the average molecular weight of carbon I. So we know that the normal paraffin molecular weight for any carbon I is given by this. So let's say that could be for C7 component, that will be the normal heptane, and normal heptane is about 100. So yeah, so if you take, like, if you put I equal to 7, you will get about 100 with this expression, minus this is the 14I plus H. So if we solve this expression here, you will get 2 minus H. And 2 minus H, that is representing the difference between the molecular weight of normal paraffin versus the single carbon number average molecular weight. So if in PVT-SIM, if it's -4, if I put -4 here, then what it is gonna suggest, then this -4 is gonna be a value of 6, and this 6 will suggest that the molecular weight of average carbon number or average single carbon number is 6 units less than its respective normal paraffin molecular weight. And that will be a constant value for all components. So the molecular weight of C7 will always be less by 6 units from normal C7, and for C8 it will be less than 6 units from its respective normal C8. So these are all limitations and assumptions in the exponential discrete model. And you will see in the gamma distribution model, there are no such assumptions. And if I plot, for example, this is log of Zi versus the difference in the carbon number. So that's how my data looks. And then what you do is you just fit a straight line through the data. So that's this straight line. That's your model. And the amount of the heaviest fraction, this is Zn plus, so n is the heaviest fraction we have. That is just calculated by 1 minus sum of all mole fractions until n minus 1. So that's the lab reported Zi, and that's what you have calculated from the model. And this is the amount of the first carbon number that comes from this equation here. And A is mainly representing the slope of this line, which is mainly a function of the average molecular weight we have seen before. So higher the average molecular weight, for example, for oils, this will be less steeper, this straight line. Yeah. Okay. So now we will discuss the gamma distribution model, which is a more general model, and that's something we use. And you can easily transform the gamma distribution model into an exponential distribution model. So yeah, so gamma distribution model, why it's called a continuous model compared to the exponential model, which was discrete, is because it is a continuous function of molecular weight. It's just a probability density function, which is a continuous function of the molecular weight, and it has 3 parameters, as Matthias said. One is the shape factor, that's this alpha, that controls the shape of the distribution. So if I plot log of Zi versus m, if alpha is equal to 1, then it's a straight line. Alpha 0.5 looks like this blue line. Alpha equals to 2 has this hump, which is the green line. And this eta, that's the second parameter in the model. That is actually the lowest molecular weight you can have in the distribution. So that's the molecular weight on the x-axis from which you are starting your distribution. And then they have the third parameter is average, which actually comes in this beta term here. And the average molecular weight, again, that will be if you are doing the molar distribution for C7 plus, then that will be the average molecular weight of the C7 plus. Okay, so that now we will discuss something that was not mentioned before, and it's because we now see that the gamma model is a continuous model, right? So this is, if you have these 3 parameters, alpha, eta, and the average molecular weight, you get this continuous distribution of the component amounts versus molecular weight. But we never use the gamma distribution model in its continuous form. We always need to discretize it to represent the different components we have. And that's the beauty of this model that you can actually discretize this continuous function in any intervals representing the different cuts or components you might have from your laboratory PVT analysis. So yeah, so the gamma model is almost never used in its continuous form. It needs discretization. Yeah, so this is maybe this looks very complicated, but the simple idea is that this continuous distribution that you see here, it needs to be discretized. And to discretize, you need some kind of boundaries. You have to specify the boundaries on x-axis, which we call as lower molecular weight. So we represent them as this MLI here. And in this monograph, it is MBI. So it's the same thing, MBI or MLI. So that's the lower molecular weight boundaries that is specified for each fraction or cut that you are interested in, and that so that will discretize this continuous function. And once you discretize it, then this area under the curve, so this shaded area, that is gonna give you the amount of that component that you are interested in, and also it also gives you the average molecular weight of that component. So this is the equation from chapter 5 in the SPP monograph. Yeah. So in summary, to use the gamma distribution model, you need 3 parameters: alpha, eta, and the average molecular weight that describes your continuous distribution. And then on top of that, you need some kind of boundaries to discretize your continuous function, which we call as lower molecular weight boundaries. And the choice of lower molecular weight boundaries depend on what kind of fractions you are interested in. If it's only single carbon number fraction, those molecular weight boundaries may be different. If those are lump fractions, for example, refinery cuts from the TBP data, those boundaries may be different. And there are different ways of finding those boundaries. And yeah. So how do we come up with the gamma model parameters? Like how we determine what's the alpha, eta, for example, average molecular weight, and these molecular weight boundaries. So the data that can be used to determine those numbers, it could be either your TBP distillation, it can be the single carbon number cuts, that is from this ASTM D2892, or it could be other cuts, for example, the refinery cuts. That's more common type of PVT data that people generally have. The process people usually have that data. But usually we recommend that if you are doing the TBP distillation, SCN cuts, the single carbon number cuts, C7, C8, C9, those are the best. And the main reason is that like it was the question before, that how you integrate the TBP data and the GC data, like using TBP data for the heavier fraction. So if you have single carbon number cuts for your TBP data, then it's much easier to integrate the TBP data and GC data together, because you have the same kind of components in both data. But if you have other data, like if you don't have TBP distillation with single carbon number cuts, still you can use the TBP data and make most of the data in the C7 plus characterization. So that's one source of data, and here we know that we get the average molecular weight. Oh, yeah, Gerardo, you have a question?
Gerardo? Microphone again. Yes.
Yeah. Okay.
There is. Yeah, I was eating, so the microphone is off.
No.
There is this rule that says, you know, when I have a subsea and I'm going to connect to a host, we try to mimic their carbon cuts, right? Their single carbon number cuts. I'm never understood the reason why, but it's a very common rule to try to have all the fields within the same single carbon number. Could you elaborate a bit on that?
Actually, unfortunately, I didn't understand the question correctly. Maybe you can elaborate.
Yeah, so let's say I have field A that I'm going to be connecting to a host that has field B, C, and D.
Okay.
And many times I'm being asked, can you do the equation of state with the single carbon numbers, cats, equal to field B, C, and D?
Yeah.
So then when we start looking at the system as a whole, it becomes easier. But I never understood the reason behind it.
Yeah.
Is it clear now?
Yeah, very good. And it's a very good and very valid question. And yeah, so
can you restate it as you see the question, Bilal, first?
Yeah, I think what I have understood from Gerardo's question is that like if you have different fields, for example, field A, B, and C, and when you are developing equation of state models, why it's generally asked or recommended to develop an equation of state model on a single carbon number basis, for example, for the different fields. Is that right?
Yes. Yeah, that is correct.
Kari, do you want to comment on it? Or
no, I think you can go ahead. I just wanted to make sure everybody was on the same.
Yeah. Okay. Yeah. So I think it's mainly because like if you have single carbon number, and that's like one reason or one of the many reasons why when we develop equation of state models, we always develop a very detailed equation of state with as many components, single carbon numbers as possible with the entire resolution that we get from the lab. Reason why it's usually recommended or it's done like that is because when you have different fields and when all the different fluids will start flowing together, then you need you need a PVT model that can describe the mixture of the different components as well. So like, for example, if you would have developed equation of state models for the different fields, and those equation of state models might have different components, like different lump components. One field A might have 11 component equation of state model where each component is different than field B. Then if you want to, if you are doing process calculation, for example, when all the streams are commingling, so for that mixture of the stream, which and each stream is coming from different field, and each equation of state model has a different component, then you would need to stack all the equation of state models together on top of each other to be able to process that mixture of the stream. I don't know, Curtis, if I explain it in an easy way, but you can comment on.
Well, there's I guess the one question is whether the fluids from A, B, and C are going to be mixing either in the reservoir or in the surface.
Yeah.
Right.
Yeah, I assume it's in the surface. Yeah.
Yeah. So if not in the reservoir, then in theory you could have somewhat different, maybe the same component molecular weights, but the properties of each component might be somewhat different. Okay. But because you need to allow the if there's mixing in the reservoir, you basically need a single component slate, right? And generally a set of properties that don't vary from area to area. If there's mixing in the reservoir, and the mixing might be happening in the wellbore or through the wellbore, right? Layers A, B, and C might not be communicating vertically, but as you start putting wellbores in there and you're commingling production from A, B, and C in a single wellbore, shut the well in, you're going to get all sorts of mixing, right?
Yeah.
Yeah.
So you need the common set of components for that reason. If it's only mixing at the surface, then you might get away with having even different equations of state for A, B, and C in the reservoir. It's not uncommon to happen that people do it that way. Whether it's necessary is another question.
Okay.
Yeah. But but in that case, if all the fluids are commingling at surface, you need a common EOS model for the surface, right?
But then you can just compound
Yeah.
the three different equations of state into one. That assumes that they're all the same, either Payne-Robinson or SRK.
Yeah.
But then you can just composite them in together in HYSYS, for example. That's very common for a lot of the companies in the North Sea. They do it that way.
Yeah, because they ask us for that, and yeah, now I understand it's out of convenience, but but it's not necessary because I didn't understand it initially.
Yeah, so if it's mixing only at the surface, then it's not necessary to have the same EOS in all the reservoirs. But if you have mixing within the reservoirs or through the wellbores, whatever, then you need to have the same equation of state, preferably the same component slate for each of the reservoirs.
Thanks, Chris. Yeah.
Very good. Yeah. So we just continue with the gamma distribution model. Yeah. So on this slide we are discussing how we determine the different gamma model parameters, and so if we have these are the two kinds of data that we can use. You can use TBP distillation data or the gas chromatography data. And in the TBP distillation data, we generally also have the average molecular weights measured. And since gamma model is giving us the average molecular weights, we can tune the gamma distribution model not just to give us the right measured good quality weight fractions, but also the measured average molecular weights. And the way we do it is if we have these kind of data, we generally tune this field-wide gamma distribution model with the alpha. That's what Matthias is trying to say. And the shape factor, the bound, and this lower molecular weight for each carbon number, they are usually the same for all the samples. So if you have like 50 or 100 samples from a given field, for all the samples, we try to have generally we try to have these three parameters same for all components, and then the average molecular weight, it will be different from one sample to another. So let's, for example, for gas condensate, it's usually smaller compared to the oils, for example. Yeah, so this is one example that's one of the studies we did, and you can see like these are the two samples. So that's you can say that's an oil sample. It should have been green, I guess. And this is the gas sample, the gas condensate, and you can see that the distribution, the Molar distribution, it has the same shape factor for the two samples. It has the same bound. The average molecular weight is actually different, and the lower molecular weight boundaries to discretize the gamma model is also the same for both. And you can see how with the same shape factor and bound, it is giving us a very good match of all the lab data. And here, like for the gas sample, you can see that the lab reported data is deviated quite a bit from the gamma model. And in that case, we can replace the bad lab reported data and trust more on the gamma distribution model, because we have tuned that model to tens and hundreds of samples that we got from that particular field. So this is one example how the gamma distribution model can be used in today's scenario when we get the extended DC distribution. It can be mainly used for quality checking the lab data and replacing the bad quality DC data. Yeah. So there are some.
Just one question before you go forward.
Yeah.
It's with regards to the alpha value. Do you have any recommendation for us to choose this value? So apart from the biodegraded oil, so we know the value is quite high. But for a normal black oil, so do you have any recommendation for that?
Yeah, so I like if that's I think what we are trying to convey. The message what we're trying to convey here is that if you have extended DC data for many samples from a field, you can actually tune the distribution model and find out what is the best shape vector that you should use for that particular field. Curtis?
Yeah, I think we have to put this in the context of people not having software that actually allow you to do the gamma modeling, the fitting of the GC data to the gamma model. There's really not any software other than the one that we use that allows you to do that.
Yeah.
And we need to respect that when we answer this question.
Yeah.
So what I would say is that you can do all of this gamma modeling in Excel. It's relatively simple. We have Excel sheets that we can exactly do this kind of process to come up with the shape and to do all of that gamma modeling outside the PVT software. That's one way to do it. If you're interested in that, then basically flag us with a mail or something, and we can have maybe an offline session on how to do that, or some of the Excel sheets that we'll be using, maybe you'll actually see how you can do that. That's one option. The other is that you simply use the laboratory data anymore. You get all this extended data. And you only use the gamma modeling to, in a sense, identify problems with the GC data and correct those problems again offline. So you correct the composition, out to C20, it's got a great fit of the gamma model, but it's falling way below the extrapolation and the data. So there's baseline shift problem, something like that. So you have an option to do, again, offline in Excel or some other program, the correction of GC data. If there's no correction needed, we just use the data. So, and then you should also be aware that PVT-SEM doesn't have anything but alpha of 1. So you don't have any real choice other than modeling it externally in Excel or something and importing that distribution into PVT-SEM. You would have to do it manually. So the option is to do it with the equations and something like Excel. We can give you a template externally to make use of it, either for QC or replacing bad data. It seems to be bad data, or going to the software that we use, the phase comp. And in that case, if you have phase comp and can do all this automated within the software, then you basically, what Bilal is saying is that you take all your GC data in and you fit to the gamma model each and every sample in a consistent way. And it becomes part of that whole EOS tuning process. So if you're using PVTP and they, I don't know what they have in the way of options, but you won't be able to do this within any of the other softwares, I think. So you have to decide what you want to use the gamma modeling for.
Yeah, thanks, Curtis. And as Curtis was saying, that this can be done in Excel, and that's something we are also aware of, that gamma modeling is generally not available in other PVT packages, like at least PVT-SIM, which most people use. So that's why, tomorrow when we do the exercise on equation of state model development, we will use a very comprehensive Excel file where we will do the entire C7 plus characterization, and that Excel file also have this gamma distribution model program in it, and we will see how we can use that spreadsheet to develop the gamma distribution model for the PVT reports we have, and that template you can also use for your other fields if you want. Okay, so I think we can move forward. Yeah, this is just a slide giving you the orientation of where you can use the gamma distribution model, and just highlighting that it can be used for the molar distribution of any petroleum mixture, whether it's a typical single carbon number compositions for the samples we have. It could be an oil-based mud composition. It can be refined residue, so you can see there are different pictures taken from the monograph. Yeah, so that's a good comment here. PVTP actually has a gamma distribution model, and there you can specify these two parameters, the alpha and the beta, which we saw before. Yeah, but again, the PVT, that's another debate. How, like in PVTP, you can see this gamma distribution model there, but they don't tell you everything about how they are using the gamma distribution model, because for the gamma distribution model, it's not just these three parameters, alpha, eta, and the average molecular weight. You also need to define the lower molecular weight boundaries, and I don't know what lower molecular weight boundaries they are using for the discretization of the gamma model. Maybe we have to go through the manuals to see how they are implementing that. Okay, and this is a and that's a good comment from Curtis, that if a software has a gamma distribution model, like for example, gamma distribution model, then you still need to know what are these gamma model parameters that you should use to define that you should use to define these define the distribution of the heavier ends, like alpha, what's the alpha factor for the given field, and the eta, the lower bound for the given field. And in that case, like FaceCom has the capability that you can use gamma model parameters as a regression to match your GC data, for example. But PVTP doesn't have that capability. So you have to use still have to use the Excel sheet to find out what are the gamma model parameters representative of your field, and then maybe use it in PVTP for the distribution. And this is again one other example of bad quality GC data. We have a gamma distribution model, and you see these components going down like this, indicating some kind of baseline shift error or internal standard error in the GC data, gas chromatography data measurement.
Just an example like that, Bilal, if just a question we typically get at this point is, how do you know in this graph right here that it's the lab data that's wrong,
yeah,
and not the gamma model?
Yeah. So, and again, that's a very good question, and we get this question a lot of time. And the reason why we suspect the lab data and we believe more in the distribution model is because we know that the distribution model that we have come up with, it is tuned to a very wide range of sample compositions. So if you have like 50 or hundreds of samples, and you have tuned your gamma distribution model with a single alpha value for all the samples and the lower molecular weight boundary for all the samples, then you know that alpha or shape factor is representative of your field. And if there are among hundreds of samples, if there are like 10 or 20 samples that are not following the distribution trend, then you start suspecting the lab the distribution.
What if you have a case where you have very few samples?
Yeah. In case of few samples, then then you should, like, few samples meaning that you have like only 2, 3 samples or 4 samples. In that case, you have to be careful in using the distribution model, like, because then you may be tuning your distribution model with data that have more uncertainty. And so in that case, we generally recommend using the lab reported data as is in the EOS model development, at least the extended GC data. without any correction from the gamma model.
Good.
Yeah. Yeah. So the Molar distribution model, gamma distribution model, that can be developed. The GC analysis, if you have DC analysis until C36 plus, for example, that is relatively cheaper compared to the DPP distillation. And these are the two different data types that you can use for the distribution model development. The exercise we have here, it's not super important to do, and then we'll just skip that. And we have a more comprehensive exercise on the gamma distribution model development tomorrow that we will go through.